It is a section 30.5 Spline interpolation. We'll begin with the lunge phenomenon. Earlier, we considered Weierstrass approximation theorem. If f is continuous over a closed interval AB, then for each choice of epsilon positive, there exists a polynomial p of x such that the difference between f and p is bounded by epsilon over the whole interval. Interpolation at equidistant points is a natural and quite common approach to construct approximating polynomials. Here, lunge phenomenon will show that interpolation can easily result in divergent approximations. Here we have the lunge phenomenon. Consider the function given in this way, defined on -1 to 1. It's a simple function. Now we choose n subinterval equidistant points from x0 to xn. x0 is -1, xn is 1. Then here the interpolating polynomial passing these points will diverge here, and fx minus pn of x, nth order polynomial, the maximum value is approaching infinity as n grows. Here we see two polynomials. The solid curve is f of x, the lunge function, and now dotted curve is 7th order interpolating polynomial, and here dashed curve is now the 10th order polynomial. If you choose 20, then this will go to over there and out of the window. So eventually, as n grows, the maximum value will approach infinity. Now here, so for the problem, we have some strategies. Change of interpolation points is the one of them. Earlier we studied Chebyshev knots, so that try to minimize the product portion in the error of interpolation error theorem. And also, we may try to do constrained minimization. For example, Hermite-like high-order polynomial can be used so that try to control the derivative to minimize the oscillation. And also, we may try to use piecewise polynomials, that is splines. So here we'll study splines. We have a definition. A partition of the interval is an ordered sequence xi such that x0 is a and xn is b, and between x0 and xn we have n minus some points. Okay. Here the numbers xi are known as knots or nodes, or sometimes we call them nodal points. Here we have a definition for spline of degree k on the interval. Here, spline should satisfy the 3 conditions. The first one is domain of the function is the interval AB, and there exists a partition of AB such that on each subinterval, so that is xi minus 1 to xi, there's ith subinterval. For each subinterval, the function must be kth order polynomial. So that's the reason we say that the spline of degree k. So it's a piecewise polynomial. Now, the third condition is the function itself and derivative up to k minus first derivative, this whole are continuous over the interval. So let's see linear splines. For linear splines, it must be defined on the interval AB, and then for partition, in each subinterval, it must be linear, and linear case 1, so that the function itself must be continuous. So that means that once the data points are given, then it is connecting the points along with a line segment. So that's the result from the definition. Here the points x0 to xn and y values. Now for each subinterval, we try to get the line segment over the ith interval. That is a slope and between 2 points, and then so that this is a line of slope point to slope form of the line. Okay, so it's passing here xi minus 1 and yi minus 1, and right side that is xi and yi. Okay, so here we see the example for this data, and x are here 0, 0.2, 0.5, 0.8, and 1, and these are y values for that one. Here, right now, the data points are this one and that one, and this one, and this one, and that. So that for each data point here, for consecutive data points, we try to connect linearly like that. So that is linear spline. Okay. For linear spline, we can analyze the error. We can find the upper bound from interpolation error theorem, and if we restrict the analysis on subinterval, ith subinterval, then here from interpolation error theorem, fx minus px will given in this way. Now here that one, okay, this one, okay, we are focusing right now here that subinterval xi minus 1, and that is xi, and now x is somewhere here, so that this distance, that distance will be a constant, already decided. This product is minimized when here this distance and that one are the same, so that eventually that one in modulus is bounded by here quarter of that squared, so that xi minus xi minus 1, half of that squared is this one, so that these are bounded by that one. And now that is f double prime evaluated at some points. So for each subinterval, we have that, so that eventually overall we have the difference is bounded by m2, which is maximum of double derivative of f, and here now and quarter and half will combine here, and we try to measure the maximum, so we reach this analysis. So if you try to choose fine points, then it'll approximate better along with the second order. Okay, now we consider quadratic splines. That is the second order. Now we deal with KS2. Here, before going to how to construct quadratic splines, we first consider this remark. Okay. Now, quadratic spline must be a piecewise polynomial of degree 2. For each subinterval, it must be quadratic, so that there are n subintervals, and each subinterval we need 3 variables, parameters to decide. So there are 3 n parameters to decide. Now, for n subintervals, here each subinterval in left edge points xi minus 1, the value is yi minus 1. Here now qi is the restriction of the quadratic spline on ith subinterval. And for qi and right end point of the subinterval is yi. So we have here 2n equations. To solve the problem, we need 3n equations. Now from here, and for each subinterval, 2 equations, so that we have 2n equations. And here now, quadratic spline, its derivative must be continuous, so that here, now that in our nodal points are given, then if this is qi, and then it's qi plus 1, then its derivative at here xi must be the same, so that qi prime at right end point of ith interval, and qi plus 1 prime at left edge point of I plus 1, I plus first subinterval, so that at xi, the derivative must be the same. So this condition, the derivative continuity condition, will make n minus 1 equations, because we have only n minus 1 interior points. So here we have 2n equations and n minus 1 internal equations, so the total 3n minus 1 equations are available, but number of parameters we have to decide is 3n. So when you try to construct quadratic the splines, you need provide one additional condition. For example, you may try to give derivative at the beginning point, or if you know the value, then you can use it. But if you don't know, and you may put this as 0, and or the second derivative can be given. Any kind of the one additional condition must be given to decide these 3n parameters. Okay, and either left-hand point or right-hand point at B, you can give an additional condition. Either way, somehow you have to give one additional condition. Okay, let's go to the construction of quadratic polynomials. First, we define zi, which is derivative of q, the quadratic spline at xi. Now, momentarily, here we assume that is known. Later on, we'll consider how to construct this, find these values. Momentarily, we assume zi is known. So at each nodal point, the derivative value is known. Then here is quadratic spline, and its derivative must be locally linear and continuous, so that here for the derivative function qi prime, okay, here we have at qi prime, that is for each subinterval here, that is xi minus 1, that is xi. Here qi is defined here, and also its derivative is defined here. Now that is linear, and left edge value, now we assumed here the values, so that the value at here left edge point is zi minus 1, and at right edge point is zi minus 1, and this is locally linear because its qi itself is quadratic, so its derivative must be linear. Okay, so for that one, we can construct the equation of the line. So at left edge point, the value is ci minus 1, and that must be the slope, and here, so that this one is the point slope equation representing qi prime, the line segment over the ith subinterval. Okay. Now, for that one, we integrate, then qi must be integration of this one and that one, and this is a constant, so that the constant times x and plus c, rather than that standard form, we write down here this way, and plus some constant k. Now we decide this k by using here left edge point at xi minus 1. The q value must be yi minus 1. These two terms will be 0 when x is xi minus 1, so that we can see easily k must be yi minus 1. So that's the reason we try to choose that form, so we can deal the terms more conveniently. Okay. So here, for each subinterval, we decided the formula for quadratic spline. Now, we have to determine zi. In the beginning, we assumed momentarily, and we know them. Now we have to decide. Here we use the continuity of q prime, and then we used also left edge value. Now, maybe we may try to use the information not yet used, that is right edge value. For the equation qi, we try to use right edge value of qi, then the height must be yi, and now we reach that one. Okay. For this one, we are moving this into left-hand side, and we reorganize in this way, so that finally, for this equation, here, yi minus yi minus 1 equal this one and average value of the z values in the subinterval. Okay. Now, if we assume z0 is given by user, then we can solve this one for zi, so that when I equal 1, that will be z0, and everything is known, and we can get z1. By using z1, we can get z2, and so on. If we specify zn, then this equation can be solved for zi minus 1, so that in decreasing order you can get zi's. Either way you can do that. for this one, we assume the Z0 is given. Then by using this recursive formula, you can decide every Z values. Now, once you decide Z values, then that is the formula for the quadratic spline. And for each subinterval, by using the Z values and the point values, you can decide that quadratic spline completely. Okay. Okay. Here, there is another one I already explained. Okay. Now, we'll consider the same data used for linear spline. Now, for this one, here, we don't know the slope value, but by using, okay, that's x0, x1, y0, y1, okay, so that here we may approximate the slope y prime at 0, okay, that one is now y change 1.3 minus, no, 3.0 is first, okay, here y change 3.0 minus 1.3 over and 0.2 minus 0.0, which is same as now 8.5. Okay, so for this value, approximated slope, we try to use this value for Z0. Then now by using this formula, you can decide the Z values, and then here now by using these Z values, you can complete this quadratic spline. So that is exactly here we can get, and then now along with the linear spline, the quadratic spline is pictured. So it's a smooth and for each nodal points, and now quite reasonable interpolation. Okay, that's the end of first part. We'll continue in the second part. Thank you.